Hello, in this presentation, I will proceed with a presentation about the paper titled Efficient Policy Adaptation with Contrastive Prompt Ensemble for Embodied Agents. The order of the presentation is as follows. First, the introduction section. I am a PhD student in the Machine Learning Lab, directed by Professor Woo Hong-wook, and our lab is engaged in research across the following areas from multitask learning, meta-learning, multimodal learning, sample-efficient offline reinforcement learning, to skill-based learning. And let me introduce myself. I am Wonjae Choi. For follow-up questions or discussions, feel free to reach out to me. My email is available for contact. My research is rooted in the fields of reinforcement learning and embodied AI. My most recent work is Efficient Policy Adaptation with Contrastive Prompt Ensemble for Embodied Agents, which is presented at International Conference of Neural Information Processing Systems. I'd like to begin by giving you an overview of the research paper we will be discussing today. What you're seeing on the screen are actual environmental results. These demonstrations show an autonomous driving agent. This agent is performing tasks in new environments shown on the right side. These environments were not encountered during its training. Remarkably, it adapts without any additional training. The reason we can create such an agent is due to the availability of data that can be pre-trained on various changes, as you can see on the left side. Each group of data is unique with different features. Just like the agent adaptation examples you see on the right side of the screen, the agents might face new situations. In these situations, all sorts of different features from the real world come together in complicated ways. We have conducted research to address these challenges. Let's delve into the abstract of our research. Our paper explores a contrastive learning-based prompt ensemble method designed specifically for embodied agents. We are investigating a method that helps agents adapt to new and complex situations. These agents are trained to handle tasks in an ever-changing world, just like humans do. However, it's hard to predict and gather data for all the ways an environment can change. That's why we suggest using a generally pre-trained model that already been trained on a range of data. We define the problem as the agents needing to cope with changes in their surroundings. These changes are mixtures of different environmental elements and physical factors of agents. To address this, the pre-trained model adapted to agent must be optimized to environment changes with limited data. Also, the agent needs to be able to tackle new challenges not seen before rapidly. This is known as zero-shot adaptation. Our goal is to create a training framework that makes this possible even when the world around the agent changes in complex ways. Now we move on to preliminary. Okay, let's introduce about what embodied AI is. Embodied AI is a field of research where artificial intelligence is embedded into robots or machines with physical forms, enabling them to perceive, act, and learn in the real environment. The goal is to extend AI's capabilities beyond mere information processing to interacting with the physical world. It utilizes sensors and mobility to navigate the environment, learns from experiences, and solves problems. This involves tackling complex tasks that combine elements of vision and language within the context of traditional reinforcement learning. Now there are some famous simulators. A simulator AI2 Thor is based on the Unity 3D game engine and features 4 categories: kitchen, living room, bedroom, and bathroom. It comprises 120 photorealistic 3D scenes. It supports various agent types and provides environments for object navigation, rearrangement, and manipulation tasks based on interactions with the environment. The simulator habitat theme is expandable with a wide variety and scale of indoor datasets, and it is a 3D simulator that applies a very high level of physical dynamics. It offers various embodied AI tasks, including navigation, instruction following, and question and answering. Alfred is an environment for embodied AI tasks based on natural language directives and visual information built on the AI2 framework. Alfred focuses on modeling the behavior of artificial intelligence agents in real-world domestic settings by providing long horizon scenarios that require complex goal achievement, multiple stages of interaction, and a high level of environmental understanding. Virtual Home is a simulator designed to simulate complex household interactions and everyday activities in a virtual environment. It provides scenarios where agents interact with various home appliances and carry out everyday activities such as cooking, cleaning, and organizing items. Now I will introducing some papers related to embodied AI and domain adaptation in R. First paper is simple but effective clip embeddings for embodied AI. For the first time, in the field of embodied AI, clip embeddings were applied to various environments and tasks, replacing the previously used ImageNet pre-trained embeddings. experimentally, it was demonstrated that clip embeddings effectively contain the primitive features required for diverse complex vision tasks. Second paper is Jetson zero-shot object goal navigation using multimodal goal embeddings. It utilized the clip space to address the problem of zero-shot transfer across modalities in visual navigation tasks. And it proposed an algorithm for zero-shot transferring an agent trained on image navigation task to the object navigation task. Third paper is Zero Experience Required Plug-and-Play Modular Transfer Learning for Semantic Visual Navigation. Basically, visual navigation tasks are distinguished based on the goal modality, presenting the issue of needing to retrain the policy for each target task. To address this, this paper proposed an algorithm capable of zero-shot transfer across 5 different goal modalities, achieved through the training of multimodal goal embeddings. Next paper is Do as I can, not as I say, grounding language in robotic affordances. It combines the feasibility of plans from LLMs, large language model, with the value function to infer executable plans for physical environments. The value function is learned in a given environment. Next paper is PALM-E, an embodied multimodal language model. It optimizes LLMs for multimodal embodied tasks by adding a vision input module to the LLM input layer. It learns task planning through text generation training on a given dataset. Next paper is LLM Planner, few-shot grounded planning for embodied agents with large language models. It identified the sample from the given example trajectories that is deemed most similar to the current task and using it as a prompt for the LLM. Utilizing the LLM for task plan inference through an in-context learning approach. This page is for domain adaptation in reinforcement learning. In vision-based RL, the method involves separating the learning of the observation encoder and the policy network. The observation encoder is trained through domain randomization or generalization method using randomly sampled images. The policy network runs the RL task using the embeddings from the observation encoder as input. And there are several papers related to representation learning. First, VAE-based state representation learning, and second is contrastive learning-based state representation learning. The following 2 pages are related to prompt learning and pertain to the methodology that will be introduced in the upcoming research content. There are 2 types of prompt learning in vision language model. Firstly, this page introduces text-based prompt learning method. First paper is Learning to Prompt for Vision Language Models. It shows a method for adapting clip to specific classification dataset, not by updating the encoders, but by placing additional learnable parameters on the text class token and finding text prompts that increase the similarity between text and image embeddings based on few-shot learning. It shows an average performance improvement of 15% across 11 different classification dataset compared to state-of-the-art methods. Second paper is conditional prompt learning for vision language models. To address the overfitting issue on scene classes of the previous paper, a proposal for input image condition text prompt learning is proposed. The enhancement in classification performance for new classes is validated through various datasets. This page is for visual prompt learning. The paper exploring visual prompt for adapting large-scale models proposes a method that involves adding learnable parameters at the pixel level to achieve an image transform effect that enhances classification performance in specific domains. Experimental results across 15 datasets show significant performance improvements on particular datasets. The second paper is visual prompt tuning. It shows a method applicable to transformer-based models that involves adding additional learnable embeddings to the existing image patch embeddings. This approach can be applied to models using transformers, enhancing performance by augmenting the original image input with image context learned for downstream tasks. Performance improvements are observed across various datasets and downstream tasks. Now I will introduce our paper, Efficient Policy Adaptation with Contrastive Prompt Ensemble for Embodied Agents. We adopted a two-step approach to tackle the challenge of sample-efficient policy learning and zero-shot adaptation for embodied agents facing complex domain variations. First, to construct domain invariant representations with respect to a specific domain vector, we propose an optimization technique based on expert data across various domain vectors using prompt-based learning methods. This technique involves training prompts to enhance the performance of the clip visual encoder for each domain vector, employing a contrastive learning objective. And to generate robust representations for complex domain variations, we propose an attention-based ensemble module. With the parameters of all trained prompts fixed, the ensemble module and policy are jointly trained within few online source domains. In deployment, a non-stationary environment where its visual domain varies according to the environment conditions and agent physical properties is considered, and the zero-shot performance is evaluated. Firstly, I will explain the prompt-based contrastive learning. Prompt-based contrastive learning aims to construct domain invariant representations with respect to specific domain vector for egocentric perception data. To do this, we adopt several contrastive tasks for visual prompt learning, which can be learned on a few expert demonstrations. We specifically adapt behavior, augmentation, and time step driven contrast tasks to generate positive visual observation pairs, as shown in the figure. Through this process, each visual prompt encapsulates domain invariance knowledge pertinent to its respective domain vector. Finally, we obtained a visual prompt pool by conducting the prompt-based contrastive learning on different domain vectors. Next, I will explain the guided attention-based prompt ensemble. To effectively integrate individual prompted embeddings from multiple visual prompts into a task-specific state representation, we devise a guided attention-based prompt ensemble structure as shown in figure, where the attention weights on the embeddings are dynamically computed via the attention module for each observation. Given observation and the learned visual prompt pool, guidance scores are computed based on the cosine similarity between the observation and visual prompted embeddings. As attention module is optimized by a given reinforcement learning task objective in the source domains, the resulting state representation tends to be task-specific, while it is also domain invariant by the ensemble of contrastively learned visual prompts based on attention module with respect to the combinations of multiple domain factors. Now we move on to evaluation section. Here I will explain experiment settings in simulation environments. Among embodied AI tasks in AI tutor, we evaluate our framework with object goal navigation and point goal navigation tasks. For zero-shot adaptation scenarios, 75 different domains are randomly generated with several predefined domain factors. For example, camera fields of view, stride length, rotation degrees, loop degrees, and illuminations. For embodied AI settings in MetaWorld environments, we slightly modified MetaWorld to have egocentric images as observations. We used tasks such as Leech and Leech-Wall for our experiments. For zero-shot adaptation scenarios, 70 different domains are randomly generated with predefined domain factors such as camera positions, gravity, wind speed, and illuminations. For the color simulator, we used two different autonomous driving maps. And to implement 50 different domains, we use camera positions, camera fields of views, weather conditions, times of day, and different ranges of action magnitudes as domain factors. A figure shows our experimental simulators, and we use AI tutor, MetaWorld, and color environments specifically configured for embodied agent tasks with dynamic domain changes. These environments allow us to explore various domain factors such as camera settings, stride length, rotation degree, gravity, illuminations, wind speed, and others. And I will explain experiment results in zero-shot adaptation scenarios. In our zero-shot evaluations, we use target domains that can be categorized as either seen or unseen. The seen target domains are those encountered during the phase of prompt-based contrastive learning, while these domains are not present during the phase of prompt ensemble-based policy learning. On the other hand, the unseen target domains refers to those that are entirely new, implying that they are not encountered during either learning phases. In various tests, including AI tutor, egocentric MetaWorld, and color, our model, Kunpei, demonstrates remarkable performance, significantly outperforming the competitive baselines in CLIP. Our model achieves higher success rates in both seen and unseen target domains, up to 5.7% in AI to Thor, 24% in egocentric meta world, and consistently maintains competitive zero-shot performance across all conditions in color. This is now the concluding section. In conclusion, we presented the CONPE framework, a novel approach that allows embodied RL agents to adapt in a zero-shot manner across diverse visual domains, exploring the ensemble structure that incorporates multiple contrastive visual prompts. The ensemble facilitates domain invariant and task-specific state representations, thus enabling the agent to generalize to visual variations influenced by specific domain factors. The direction of our future work is to adapt the framework with semantic knowledge based on pre-trained language models to improve the policy generalization capabilities for embodied agents in dynamic complex environments and to cover various scenarios associated with multimodal agent interfaces.